Most of us share a pretty basic intuition about how things break. We expect a warning, a strange noise, a flashing light, some clear signal that something is going wrong. And this intuition feels so right, so fundamental, that we almost never stop to question it. But what if that very intuition is what makes us blind to some of the most dangerous kinds of failure?
Our default mental model is really simple. As a problem gets worse, the warnings should get louder, right? More stress on a system should equal more signals, more frequent alerts, more obvious signs of trouble. We instinctively expect a system to scream when it's under strain.
But the reality is often the exact opposite. The very structures that make a system run smoothly under normal conditions can, when placed under stress, begin to muffle, distort, and eventually completely silence the warnings they were designed to give us. And this creates a really dangerous paradox. We're waiting for the signals to get louder as the stress goes up. But in many complex systems, as that stress increases, the number of accurate warning signs actually starts to decrease, sometimes falling to nearly zero right before a catastrophic failure. Now, this isn't some random glitch, it's a structural feature. To really get why this happens, we need to build a simple system from the ground up and watch how its own logic leads it to fail.
Okay, so let's imagine a very simple system. We have a heavy, flat platform. Its one and only job is to stay perfectly level. That's it. And this platform is being held up by several supports. Let's take a closer look at each piece.
First, you've got the platform itself. We'll call this the load. It represents the system's core, non-negotiable goal, the main objective it's built to maintain at all costs. In an organization, that could be anything from hitting a quarterly target to delivering on a public promise. But for our model, its goal is just to stay level.
Holding up the load are the supports. You can think of these as the resources, the teams, or the components that do the actual work. They provide the constant upward pressure that keeps the load stable.
And then we have the controller. This is our decision-making function. It could be a manager, an automated process, whatever. Its only job is to watch the system and adjust the individual supports to make sure that load stays perfectly level.
And finally, we have the signals. See, the controller isn't all-knowing. It completely relies on these pressure gauges to understand what's happening in each support. These signals are its only connection to reality, its only way of seeing the system. So when the system is healthy, the feedback loop is clean and simple. The controller sees a tiny imbalance from the signals, it adjusts the pressure in the supports accordingly, and then it checks the signals again to confirm that everything is stable. The system is in a perfect state of equilibrium.
So our system is stable and everything's working as it should. But now, let's introduce a tiny, localized bit of stress. What you're about to see is that the system's response is going to be completely rational, and yet, it's that very rationality that will plant the seeds for its own failure.
Okay, so a very slow, almost unnoticeable leak starts in one of the supports. Its pressure starts to drop, which means it can't hold up its share of the load anymore. Now, the controller immediately detects the tiny tilt this causes, and following its core mission, it does the perfectly logical thing. It increases the pressure in the other, healthy supports. This extra pressure easily compensates for the weak one, and just like that, the load is perfectly level again.
From the controller's point of view, everything is fine. The primary goal, keeping the load level, is being met. A problem was detected, and it was corrected. But of course, this appearance of health is just an illusion. It's been bought by shifting the strain and creating a hidden vulnerability somewhere else in the system.
This is the logic of local response in action. The system fixes the immediate visible problem by compensating. Think about a project team that's falling behind. They might just redefine a major delay as a scope change to keep their status report green. The indicator looks good, but the project is actually in deeper trouble. The root cause is still there, and now other parts of the system are under more strain.
Now, this whole strategy of compensating locally seems to work, but it hinges on one critical assumption. It assumes that the signals coming from the supports are always reliable, and that assumption is about to break.
Remember that one support with the slow leak? Well, it's now being pushed harder and harder by the controller to compensate. The strain on that single component eventually becomes too much, and its pressure gauge, its signal, breaks. But here's the crucial part. It doesn't just go dark. It fails by getting stuck in the green or normal position.
This is a mechanism called signal suppression. And notice the incredible paradox here. The component that is under the most stress, the one that most needs to scream for help, is the very first one to stop sending accurate warnings.
The system has effectively muted its own most important alarm.
And this leads to a deeply counterintuitive result. It was the controller's completely rational attempt to fix the problem, by increasing pressure, that created the very conditions that broke the signal. The act of compensation is what ultimately silenced the warning. The local solution has hidden the global problem.
So now, our controller is effectively flying blind. It's operating with incomplete and deeply misleading information. It looks at its dashboard and sees a row of perfectly healthy supports, because one of its key indicators is now actively lying to it.
So you have this huge gap that opens up. The controller's perceived reality is one of total stability and success. All signals are green. But the actual state of the system is one of growing danger. One support is nearing total failure, and the others are being strained to their absolute limits to pick up the slack.
This situation creates what's known as an escalation of commitment. See, the controller isn't being stupid or irrational. It's just following the data it has, and every piece of data it sees is telling it everything is fine, keep going. The system starts to double down on a failing strategy, precisely because its own broken feedback loop is telling it that the strategy is working perfectly.
When you combine these two forces, signal suppression and escalation of commitment, you create a clear pathway towards a system-level failure. And this failure won't be the result of one big mistake, but of a whole sequence of small, locally rational decisions that are made within a completely broken information structure.
So let's trace the anatomy of the collapse. First, the performance indicators become misleading. They show success where there's actually a growing fragility. Then, the channels for negative feedback get suppressed, especially from the parts of the system under the most stress. This, in turn, leads to an escalating investment in a strategy that isn't working, because there's no data telling the controller to change course. And the final result is a massive, system-level failure that seems to come out of nowhere, but was in fact the gradual, logical outcome of the system's own internal dynamics.
And this forces us to completely reframe what we mean by failure. The collapse wasn't really caused by one faulty support. It was caused by a failure in the information that connects the different parts of the system. The components didn't fail the system, the broken signals did. The system becomes blind and deaf, operating perfectly according to a reality that isn't real, right up until the very last moment when it all comes crashing down.